Advanced integration, substitution and partial fractions. Okay, so let's begin with advanced integration, specifically looking at techniques involving substitution and partial fractions. As you recall from our previous work, a key skill we developed was partial fraction decomposition, or PFD for short. We learned how to break down complex rational functions, that is, fractions with polynomials in the numerator and denominator, into simpler fractions that are much easier to integrate. However, not every integral comes neatly packaged for us to apply PFD directly. In many more challenging problems, the function you're trying to integrate, what we call the integrand, isn't immediately in a form where we can just jump into partial fraction decomposition. That's where the techniques we'll cover in these next few slides come in. When the integrand isn't quite ready for PFD, we often need a stepping stone, a way to transform it into a suitable form. We achieve this using substitution. Think of substitution as a bridge. It helps us get from the complicated integrand to one where we can successfully apply partial fraction decomposition. Now, there aren't just one, but two main strategies we'll explore to handle these more complex integration problems. We'll look at each of these in detail, with examples, so you'll be able to recognize when to use each one. We'll start by looking at how to use substitution specifically to prepare an integrand for partial fraction decomposition, and then we'll move on to a combined approach where substitution transforms the entire integrand into a rational function. Strategy 1. Substitution for decomposition. Essentially, this strategy comes into play when the integrand, that's the function we're integrating, looks almost like a rational function, meaning a fraction of polynomials. But often, the powers of x are making it tricky to directly factor the denominator. The core idea here is to use a substitution to simplify the algebraic structure. We'll transform the integral into a form where we can apply partial fraction decomposition, and then, crucially, we'll switch back to our original variable before we finish the integration. Think of substitution as a temporary detour to make the problem easier to solve. First, identify the pattern. We're looking for a repeating term within the integrand. This could be something like x squared or x cubed. The goal is to find something that, if we replaced it with a single variable, would turn the whole expression into a standard rational function. Next, apply substitution. Once you've spotted that repeating term, you substitute it with a new variable. For example, you might say, let x squared equal y, this is where the simplification begins. Then, algebraic decomposition. This is where we finally get to use our partial fraction decomposition skills. But now, instead of working with x, we're working with the new variable, y. After that, restore the variable. Don't forget, once you've decomposed the function in terms of y, you need to replace y with its original expression in terms of x. This brings us back to the original variable we started with. Finally, integrate. Now that you have a simplified expression, you can integrate it using the standard integration formulas we've already learned. Let's illustrate this with an example. We want to evaluate the integral of 1 over x times x to the power of 4 plus 1, with respect to x, that is, integral of 1 over x multiplied by x to the power of 4 plus 1 dx. Step 1. Prepare the integrand. Now, this is a clever trick. To make the substitution easier, we're going to multiply both the numerator and the denominator by x cubed. This gives us the integral of x cubed over x to the power of 4 multiplied by x to the power of 4 plus 1 dx. This might seem strange, but it sets us up nicely for the substitution in the next step. It doesn't change the value of the integral, just its form. Okay, so let's move on to our first advanced integration strategy. As we discussed in the previous slides, sometimes we encounter integrals where the function isn't immediately ready for partial fraction decomposition. This slide, titled Strategy 1, Substitution for Decomposition, shows us how to handle those situations. Now, let's break down the step-by-step process. Strategy 1, Substitution for Decomposition, continued. Now, step 2, substitution. We're going to make a substitution to simplify things. Let's set y equal to x to the power of 4. Remember, our goal is to get this integral into a form where we can easily apply partial fraction decomposition. Now, because we've defined y in terms of x, we need to account for this when we integrate. So we differentiate both sides of the equation x to the power of 4 equals y. With respect to x, this gives us 4 times x cubed dx equals die. But we don't want 4x cubed dx in our integral, we want just x cubed dx. So we divide both sides of that equation by 4, giving us x cubed dx equals 1/4 die. This is a crucial step. It tells us how our differential changes with the substitution. Now, let's substitute this into our integral. Remember, our integral was 1/4 integral of x to the power of 4 times x to the power of 4 plus 1, with respect to x and dx. Now, we replace x to the power of 4 with y, and x cubed dx with 1/4 die. This transforms our integral into 1/4 integral of 1 over y times y plus 1, with respect to y. Notice how much simpler this looks. Moving on to step 3, partial fraction decomposition. Now that we have a rational function in terms of y, we can decompose it. We want to express 1 over y times y plus 1 as the sum of two fractions, a over y plus b over y plus 1. To find a and b, we multiply both sides of the equation by y times y plus 1. This gives us 1 equals a times y plus 1 plus b times y. Now, we solve for a and b by strategically choosing values for y. If we let y equal 0, the equation becomes 1 equals a times 0 plus 1, which simplifies to a equals 1. Next, let's let y equal -1. The equation becomes 1 equals a times -1 plus 1 plus b times -1. Since a is 1, this simplifies to 1 equals -1 plus 1 minus b, which means b equals -1. Therefore, our partial fraction decomposition is 1 over y times y plus 1 equals 1 over y minus 1 over y plus 1. Finally, step 4. Restore the variable and integrate. Now that we've decomposed the fraction, we can substitute it back into our integral and integrate. So, we have 1/4 integral of 1 over y minus 1 over y plus 1. With respect to y, the integral of 1 over y is the natural logarithm of the absolute value of y, and the integral of 1 over y plus 1 is the natural logarithm of the absolute value of y plus 1. So, we get 1/4 times the natural logarithm of the absolute value of y minus the natural logarithm of the absolute value of y plus 1, plus the constant of integration. See, we can combine these logarithms using the logarithm property to get 1/4 times the natural logarithm of the absolute value of y divided by y plus 1, plus c. But remember, we made a substitution at the beginning where we set y equal to x to the power of 4. So, we need to substitute back in to express our answer in terms of x. Replacing y with x to the power of 4, we get our final answer. 1/4 times the natural logarithm of the absolute value of x to the power of 4 divided by x to the power of 4 plus 1, plus c. And that completes the integration. Remember, the key here was using substitution to transform the original integral into a form suitable for partial fraction decomposition. We'll see similar strategies used in more complex problems, so it's important to understand this process thoroughly. Okay, let's continue working through this integration problem. This is slide 3, and we're building on what we started on the previous slide, where we prepared the integrand by multiplying both the numerator and denominator by x cubed. Strategy 2, Combined Substitution and PFD. Okay, so let's move on to our second main strategy for advanced integration. As we discussed earlier, sometimes we encounter integrals where the function isn't immediately set up for partial fraction decomposition. And sometimes, the integrand isn't even a rational function to begin with, meaning it contains things like trigonometric functions, exponents, or other transcendental functions. This slide details strategy 2, which is all about combining substitution with partial fraction decomposition. The core idea here is to use a clever substitution to transform the original integrand, the function we're integrating, into a rational function. Once it's rational, we can then apply the partial fraction decomposition techniques we learned previously. And finally, after integrating, we'll substitute back to express our answer in terms of the original variable, x. Let's break down the step-by-step process. First, choose a substitution. We need to pick a substitution, a replacement, that will simplify the integrand. I've given a couple of examples here. You might let u equal sine of x, or u equal e to the power of x. The goal is to choose a u that turns the trigonometric or transcendental part of the function into something more manageable, ideally a polynomial-like expression. Next, and this is crucial, transform the differential. Remember that when you substitute, you don't just replace x with u. You also need to change dx, the differential, into its equivalent in terms of do. This means finding the derivative of your substitution and rearranging to solve for dx. For example, if u equals sine of x, then the derivative of u with respect to x is cosine of x, which means dx is equal to do divided by cosine of x. Don't forget this step. It's a very common mistake. Once you've done that, perform PFD. Now that your integral is expressed in terms of u, it should be a rational function. This means you can now apply the partial fraction decomposition technique we covered earlier to break it down into simpler fractions. Then, integrate in terms of u. Now that you have the decomposed form, you can integrate each term with respect to u using standard integration formulas. Things like the integral of 1 over u is the natural logarithm of the absolute value of u, and so on. Finally, final back substitution. After you've integrated with respect to u, you need to substitute back to express your answer in terms of the original variable, x. Replace every u with whatever you originally defined it to be. Let's look at an example to illustrate this. We want to evaluate the integral of cosine of x divided by sine of x times 1 plus sine squared of x with respect to x. Step 1, substitution. We'll let u equal sine of x then, taking the derivative of u with respect to x, we get do over dx equals cosine of x. Rearranging this, we find that do equals cosine of x dx. Step 2, transform the integral. Now we substitute. The integral becomes the integral of 1 over u times 1 plus u squared. With respect to u, notice how we've successfully transformed the original integral into one involving only u, and it's now a rational function. This sets us up perfectly for partial fraction decomposition. Strategy 2, combined substitution and PFD, continued. Okay, let's continue working through this problem. We've successfully made our substitution, u$ equals sine of x$, and transformed our integral into an expression involving just u$. Now, we're at step 3, partial fraction decomposition. As you recall from our earlier lessons, before we can integrate a rational function, we often need to break it down into simpler fractions. Looking at our integral, we have 1 over u$ times 1 plus u$ squared. Notice that the denominator factors nicely. We have a linear factor, just u$, and an irreducible quadratic factor, 1 plus u$ squared. It's irreducible because it doesn't have any real roots. So we set up our partial fraction decomposition like this. 1 over u$ times 1 plus u$ squared equals a over u$ plus bu$ plus c $ over 1 plus u$ squared. Remember, because we have that quadratic term in the denominator, the numerator must be linear. That's why we have bu$ plus c $ and not just a constant. Now, to solve for a $, b$, and c$, we multiply both sides of the equation by u$ times 1 plus u$ squared. This gives us 1 equals a times 1 plus u$ squared plus bu$ plus c$ times u$. Let's expand that right side. 1 equals a plus a u$ squared plus bu$ squared plus q$. Now, let's group like terms. 1 equals a plus b$, u$ squared plus q$ plus a $. This is where equating coefficients comes in. We compare the constant terms on both sides. The constant on the left is 1, and on the right it's $1. Therefore, $1 equals 1. Next, we compare the coefficients of u$. On the left, the coefficient of u$ is 0, and on the right, it's c$. So, c$ equals 0. Finally, we compare the coefficients of u$ squared. On the left, the coefficient is 0, and on the right, it's a plus b$. This gives us the equation 0 equals a plus b dollar. Since we know a dollar is 1, we have 0 equals 1 plus b dollar, which means b dollar equals negative 1. So, we found that a dollar equals 1, b dollar equals negative 1, and c dollar equals 0. This means our partial fraction decomposition is 1 over u dollar minus u dollar over 1 plus u dollar squared. Now, let's move on to step 4, integrate in terms of u dollar. We now have the integral of 1 over u dollar minus u dollar over 1 plus u dollar squared, with respect to u dollar. The integral of 1 over u dollar is simply the natural logarithm of the absolute value of u dollar. For the second term, the integral of u dollar over 1 plus u dollar squared, we can use a simple substitution. The derivative of 1 plus u dollar squared is 2u dollar, so we need to adjust for that. The integral becomes 1/2 times the natural logarithm of the absolute value of 1 plus u dollar squared, plus the constant of integration, c. Combining these, we get the natural logarithm of the absolute value of u dollar minus 1/2 the natural logarithm of the absolute value of 1 plus u dollar squared, plus c dollar. We can also rewrite this, using logarithm properties, as the natural logarithm of the absolute value of u dollar divided by the square root of 1 plus u dollar squared, plus c dollar. Finally, in step 5, we need to back substitute. Remember that we originally let u dollar equal sign of x dollar. So, we replace every u dollar in our result with sign of x. This gives us the final answer, the natural logarithm of the absolute value of sign of x dollar divided by the square root of 1 plus sign of x dollar squared, plus c dollar. And that completes the problem. Remember, the key here was recognizing when and how to use substitution to prepare the integral for partial fraction decomposition. We'll be looking at more examples in the following slides, so make sure you understand each step. Key takeaways. Okay, let's recap the key takeaways from what we've covered on advanced integration using substitution and partial fractions. This slide is really about solidifying your understanding of when and how to apply these techniques. First point, substitution as a tool. It's crucial to understand that substitution isn't always the very last thing you do. Often, it's a preparatory step. Think of it as building a bridge. We use substitution to transform a complicated integral into a form that then allows us to use partial fraction decomposition. We're not necessarily solving the integral with the substitution itself, but rather preparing it for the next step. Remember, in our examples, we used substitution to get to a rational function before applying PFD. Now let's talk about algebraic versus functional substitution. We essentially used two main strategies, right? Strategy 1 and Strategy 2. This point clarifies when to use each. If your integrand, that's the function you're integrating, is primarily algebraic, meaning it involves polynomials and rational functions, but has some tricky powers of x, like x squared or x to the power of 4, then use strategy 1. We're simplifying the algebraic structure with substitution. On the other, and if your integrand contains trigonometric functions like sine and cosine, or exponential functions, or any other transcendental function, then you should use strategy 2. These are functions that aren't algebraic. They go beyond just polynomials and fractions. We're transforming the entire integrand into a rational function using substitution. Finally, and this is extremely important, the differential. Always remember to transform dx into do or die after you've made your substitution. This is where students most often make mistakes. If you have u equals a function of x, then do equals the derivative of that function with respect to x, multiplied by dx. So, when you substitute, you must replace both x and dx with their equivalents in terms of u and do. Forgetting to change dx will completely invalidate your integration. It's a small detail, but it's a very common error that leads to incorrect results. Keep these takeaways in mind as we move forward, and you'll be well equipped to tackle even more complex integration problems. On the next slide, we'll look at some common mistakes to avoid, building on these key points. Common mistakes. Okay, let's move on to the final slide, which highlights some common mistakes students make when tackling these advanced integration problems. It's good to be aware of these before you get stuck, so you can avoid them. 1. Ignoring the differential. This is a really frequent error. Remember, when we perform a substitution, like letting u equal sine of x, we aren't just changing the variable inside the integral. We're also changing how we express the dx, which represents an infinitesimally small change in x if we have u equals sine of x. Then the derivative with respect to x is cosine of x. This means do, the infinitesimally small change in u, is equal to cosine of x times dx. Therefore, dx becomes do divided by cosine of x if you simply replace sin x with u and forget to change the dx accordingly. Your integral will be incorrect. It's a small step, but a crucial one. 2. Premature back substitution. This one's about order of operations. It's tempting to immediately substitute back to the original variable as soon as you've made the substitution. But resist that urge. You need to fully complete the partial fraction decomposition and the integration in terms of the new variable, in this case, u, before you switch back to x. Think of it like this. You've translated the problem into a language you understand better, you solved it, and then translated the solution back into the original language. Don't translate mid-process. 3. Incorrect PFD form. This relates specifically to the partial fraction decomposition itself. When you have an irreducible quadratic factor in the denominator, something like 1 plus u squared, you cannot simply use a constant in the numerator. The numerator must be a linear expression, meaning something like a u plus b. So, instead of writing the partial fraction as a divided by 1 plus u squared, you need to write it as a u plus b divided by 1 plus u squared. This is because the quadratic factor requires a linear term in the numerator to properly decompose the fraction. It's a key rule to remember for accurate partial fraction decomposition. So, keep these 3 points in mind as you practice, and you'll be well on your way to mastering these advanced integration techniques. Remember, practice is key.